We're going to go over some basic set notation to get us started. Okay, so if we just focus on this example here. So we've got the curly brackets. Curly brackets just mean we've got a set. So an open curly bracket, start of the set, closed curly bracket, end of the set. So then we've got x colon x is greater than 4. Well, what does that mean? So it means the set, so if I just write this out, the set and the x colon x greater than 4 bit, the colon means such that. So it's x such that x is greater than 4. So it's the set of x is greater than 4. So if we think about the integers of that set, what integers are greater than 4? 5, 6, 7, 8. So the numerical answer would be 5, 6, 7, and so on. So we could just write dot, dot, dot. Okay, so how about this one? So we've got the set and x such that x is less than 7. Well, that's the set of x is less than 7. So what integers would satisfy that? Or what integers could we have in that set? So really, really bad bracket that was then. Well, integers that are less than 7. So we could have 6, 5, 4, and so on. Okay, what about this one here? So we've got the set where x such that x is greater than or equal to 4. So what integers can we have in that set? Well, we could have 4, 5, 6, 7, and so on. So it's nearly the same set as what we've got above, obviously, but this is greater than, so we can have 4 in that set. So they're almost the same set, but not quite. Okay, what about this set here? So we've got x such that x is less than or equal to minus 6. So what integers are less than minus 6? And including minus 6, we can have minus 6, we can have minus 7, minus 8, and so on. Close that. And then for this bottom set here, so we've got the set x such that x lies between 4 and 8. So what integers can we have in that set? Well, we can't have 4 because there's no equal to. We can't have 8 because there's no equal to. So we can have 5, 6, and 7. So they're the integers that belong in that set. So I want to talk about something that I touched on in the last part of the video, and that's about these sets. So these sets are almost, they're very nearly the same set. One is x is greater than 4 and one is x is greater than or equal to 4. So when we draw and write these sets out, well, what is this set? X is greater than 4, well, it will be the set of 5, 6, 7, and so on. So dot, dot, dot. And then what is this set? So if I just write equals to, so what is this set here? Well, that is the set of x is greater than or equal to 4. So x such that x is greater than or equal to 4. So that would be 4, 5, 6, 7, so on, and so forth. So now we look at these sets. So this set we've got 5, 6, 7, and so on. This has got 4, 5, 6, 7. So they're almost very nearly the same thing. This is the same as this set. It's just that this set on the left here doesn't have 4. So what we can write is we can write this. So 5, 6, 7, dot, 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 is a subset. So subset is this notation here. So this. So this means that this is a subset of the set 4, 5, 6, 7. So what does a subset mean? Well, it means that nearly the same amount of things in this left-hand set are in this right-hand set. So a sub, so think about subtraction, things get smaller, sub being smaller. So it's a smaller set of this one. So they're almost the same thing, they're almost identical. It's just that this set on the left doesn't have a 4. So we can write this, which means subset. So we can write for the original set as well. So the original set we had x such that x was greater than 4. It's getting a bit ahead of myself there. Is a subset of this set x such that x is greater than or equal to 4. Like that. Okay, so we've got the sets A. A is x such that x is less than 5, and B is the set x such that x is less than 3. So what do these sets look like? Well, A will look something like, well, less than 5, the integer is less than 5, so 4, 3, 2, and so on. And then B is going to be the set, so x such that x is less than 3, well the integer is less than 3, so that would be 2, 1, 0, minus 1, and so on. So dot dot dot. Okay, and then there's a special piece of set notation which is called union. So it's a U like that, union. And you may have seen this before if you looked at Venn diagrams. So very quickly, for a Venn diagram, so if we've got a Venn diagram like this, union means everything in the Venn diagram. So it means everything in this circle here, everything in the intersection part here, and everything in this circle there. So that's what union means. So we can apply this to sets as they are. So if we want to work out what A union B is, well, it means we want everything that is in A and B. So A union B is everything that is in the sets A and B. So we just combine the sets together. So 4, 3, 2, obviously 2's in B, 2's in A as well. 1, 0, minus 1, and so on. But what, obviously there are, if we keep going here, minus 15 will be in A, but minus 15 will also be in B. Because A was the integers less than 5, and B was the integers less than 3. So, in fact, all of the negative numbers will be in A and B. So we don't have to write them twice, we only have to write them once. So that's A union B. We can also have this symbol, which is the upside down version of union. And so you can kind of think of it, I suppose, as an N, and it's called intersection. So with our Venn diagram, the intersection part is the part in the middle where the two circles intersect. So this is the intersection part. What does that mean? Well, it's things that are common to both. So if we want to find what A intersect B is, well, we need to look at things that are common in both of these sets. So common in both of these sets. So is 4 in both of these sets? No. Is 2 in both of these? Sorry, is 3 in both of these sets? No. Is 2? Yes, it is. Will 1 be in both of these sets? Well, it'd be in this one because it's the integers less than 5, and it's in this one. Will 0 be in this set? Well, yeah. Integers less than 5. Yep, it's in this one. So we find that everything less than 2 So every number less than 2 would be in the set A intersect B. Okay, so now we've got both of these. I just want to return and think about a potential answer. So what is this set that we have for the union? We've got 4, 3, 2, 1, 0, minus 1. Well, it's all the integers that are less than 4. So could we not write that this set is x such that x is less than 4? Because that's what we've got in the set, so we can write it algebraically. So what about the A intersect B? Well, it's all the integers that are less than 2. So this set here is x such that x is less than 2. Like that. So what have we done there? Well, we've looked at two special symbols for sets, so union and intersection. We've found out what the union intersection of the sets A and B are. So we've worked the numbers out to do that. And then we've just written our answer in proper sort of mathematical notation, if you like, with how we started. So we'll look at some more examples of this. So now I've changed what the sets A and B are. So A is now the set where x such that x is greater than 6, and B is the set x such that x is less than 2. Okay, so what are A and B in numbers if we want to get rid of the mathematical notation? That was a really bad set. It's better. So x is greater than 6. What's that? Well, the integer is greater than 6, so 7, 8, 9, and so on. What is the set B? Well, it's the integers less than 2. So 1, 0, minus 1, and so on. Okay, so what would A union B be now? So remember what union means. It means that everything that's in A and everything that's in B in the same set. So what's in A? Well, we've got 7, 8, 9, 10, 11, 12, and so on. And what's in B? Well, we've got 1, 0, minus 1. So if I start writing this way, so if I just put a dot, dot, dot to begin with, so we can have minus 2, minus 1, 0, 1. Can we have 2, 3, 4, 5, and 6? Well, those numbers don't appear in A or B, so no. So the next number that we can have is 7, 8, 9, 10, and then dot, dot, dot. So essentially, that set is all the numbers, but without 2, 3, 4, 5, and 6. So 2, 3, 4, 5, and 6 aren't in that set. Okay, and then we look at the intersection. So A intersect B. So what can we have in that set? Well, is there anything that's common to both A and B? Well, these numbers increase from 7, and these numbers decrease from 1. So there isn't anything common to both. So what do we write there? And that looks like this. It's an empty set, there's nothing in the set, so we can display our empty set like this. So the set brackets, but with nothing in. So it means the empty set. And I've changed what the sets A and B are. A is now the set x such that x is greater than or equal to 4. So what is that set? Well, we can just fill what that is. So the integers greater than 4 and including 4. So 4, 5, 6, 7. And obviously it keeps going beyond that. And then what is b? Well, b is x such that x is greater than 7. So we're not including 7 because we haven't got the equal to part. So 8, 9, 10, and so on. That was a really bad curly bracket. It's better. Okay, so let's have a look at A union B. So what does union mean again? Well, it means everything in A and everything in B. So what's in A? So we've got 4, 5, 6, 7. And then in B, we've got 8, 9, 10, and so on. Okay, so can we write this set algebraically with some algebra? Of course we can. So what have we got here? Well, we've got 4, 5, 6, 7, 8, 9, 10. So that is just the set. Well, it's the set A. It's all the integers that are greater than 4 and including 4. Okay, and then what about A intersects B? Well, let's remember what A intersects B means. It means, with our Venn diagram, it means this part in the middle. So not everything that's in A and B, but just the things that are the same, so intersect. So what are the same things in A that are in B? So is 4 in A and B? No, it's only in A. Is 5 in A and B? No. Is 6 in A and B? No. Is 7 in A and B? No. Will 8 be in A? Well, yeah. Is 8 in B? It is. So we can have 8. Will 9 be in A? It will, and it's obviously in B. Will 10? Yeah. Will 11? Yep, so you get the picture. So they're the things that appear in both A and B. Well, that is just the set B, because it's the integers that are greater than 7 and not including 7. So that set there, A intersect B, is just what we started with. Thing I want to talk about. So if we've got the set A, so A, and then it's the set X such that X is greater than 5. So what will A look like? It will be 6, 7, 8, 9, and so on. Okay, and then what I want to look at is something called complement. So when we've got A with a little dash above here, that means complement. So A complement is everything that isn't in A. So if we're thinking about the integers, what integers aren't in A? Well, we can have 5, 5, 4, 3, 2. So we get the idea. So that's everything that isn't in A. And then we ask ourselves, well, what is that? Well, that set there is the set X such that X is less than or equal to 5. So A complement, so the dash means complement, everything that isn't in A. So let's have a look at another example. If we've got the set B, and let's say that B is the set X such that X is less than 3. Well, what is that set numerically? Well, the integers less than 3 are 2, 1, 0, -1, and so forth. So we'll draw our set brackets as well. Okay, so then if I want B complement, I want everything that isn't in B Well, what haven't we got in B? Well, we haven't got 3, 4, 5, 6, and so on. So what is that set now? Well, it's the set X such that X is greater than or equal to 3. So what have I done with both of these examples? Well, I've took the sets, wrote out what they are numerically, then took the complement of the set. So complement means everything that isn't in the set. So if we're thinking about the integers, what integers don't appear in this set? And then upon finding those, I've just written back in a mathematical form, so in some mathematical language, what that set is. So that's everything that I want to cover in the video. I just want to end with just a little recap of what we looked at. So we've looked at set notation, so we've looked at things like this. So this is a set, so X, and the dot dot obviously meant such that. So for this example, let's go for this, so X is greater than 7. So what does that mean? Well, it's the set where X is greater than 7. So that set would be equal to, 8, 9, 10, and so on. Okay, then we also looked at this symbol, which meant union. So from our Venn diagram, that means everything in this circle, everything in the bit where the circles overlap, and everything in there. We also looked at intersection, and what did that mean from our Venn diagram? Well, think where the circles intersect, so it meant there. We also looked at this notation, which was the subset. So if we've got the set 1, 2, 3, 4, 5, well then we could write that 1, 2, 3 was a subset of 1, 2, 3, 4, 5. What does a subset mean? Well, obviously back from where we did it in the video, it means that it has some of the elements from the original set. So 1, 2, 3 is a subset of 1, 2, 3, 4, 5 because there are some of the elements from that original set there. And then the last thing we looked at was the symbol complement. So if we had the set A, and that was X such that X was less than 3. Sorry, X was greater than 3, sorry. Then if we took the complement of that, so complement was the dash, then it would be everything that isn't in this set. So everything that isn't in X is greater than 3, so that would be 3, 2, 1, and so on. So that would leave us with this, which is the set X, such that X is less than or equal to 3. Like that. That was just a bit of a recap, just to end the video.